Here is a simple idea, but it catches almost every student off guard. A particle is accelerating whenever its velocity is changing in time, and the acceleration is the rate at which the change occurs. Well, you might say it sits perfectly well with you. To this, I would say, read the sentence again, because a trap is hiding in plain sight. Remember, velocity is a vector. It has magnitude and direction. So, if the magnitude of velocity changes, we know that the particle is accelerating, but a particle can accelerate even if its speed is constant. How? By changing its direction. If the direction changes, the velocity vector changes, which means the particle is accelerating. So, picture a race car on a perfectly circular track going at exactly 200 kilometers per hour, and the speedometer stays at this value. Most students, when asked whether the car is accelerating, say no, because nothing on the dashboard is changing. But the car is accelerating at every instant because the direction of its velocity is changing at every instant. And this acceleration due to direction only change is what we will later call centripetal acceleration. And we will come back to this kind of acceleration when we study circular motion later in the course. So simply put, if you change the direction of a vector, you have a new vector, even if its magnitude remains the same. And you must hold on to that idea because it is the single most important thing in this lesson. So more formally, we can say that when the velocity of a particle changes from v1 to v2 over a time interval delta t, we define the average acceleration during that interval as A average is equal to delta v upon delta t is equal to v2 minus v1 upon delta t. And here are two things to notice. First, the numerator is a vector subtraction. We cannot just subtract two numbers because v1 and v2 might point in different directions. Or simply put, they are vectors and you cannot do an algebraic operation on them. Second, we are dividing a vector by a scalar. That means the direction of A average is exactly the direction of delta v, because dividing a vector by a positive scalar never changes a vector's direction. It only changes its length. Now, this has consequences that trips up almost everyone the first time. The average acceleration vector does not point where the particle is going. It points in the direction the velocity is changing. Let us walk through a concrete example. A car is moving along a curved road. At time t1, it is at position p1 and velocity v1. A little later, at time t2, it is at position p2 and in a different direction with velocity v2. To find the average acceleration between p1 and p2, we need delta v, which is v2 minus v1. Here is how we do that subtraction graphically. Draw v2, then draw the reverse of v1, which we call minus v1, same length as v1 but pointing the opposite direction. Add v2 and minus v1 using the tip to tail method, or if you're comfortable with parallelogram method, you could do that as well. Then the resultant is delta v. Now divide that delta v by the time interval delta t to get A average. And you see the direction of A average is the same as the direction of delta v. Remember, average acceleration tells us what happened on average between 2 points. And before we go further and look at a single instant, that is acceleration at a point of time, let us see how the acceleration breaks into components, because this is what makes 2D problems tractable. So just as we break velocity into x and y components, we break acceleration into x and y components. That is, ax is equal to delta vx upon delta t, the rate of change of vx, and ay is equal to delta vy upon delta t, the rate of change of vy. And here is a powerful part. The acceleration in the x direction depends only on how vx is changing. The acceleration in the y direction depends only on how vy is changing. They do not interfere with each other. And this is the same independence you saw with velocity components. And it is what makes 2D problems solvable. So you solve the x direction and the y direction separately, then combine at the end if needed. So here the magnitude of the full acceleration vector is under root ax square plus ay square. And its direction is given by the angle theta is equal to tan inverse of absolute value of ay upon absolute value of ax measured from the plus axis, then adjusted for the quadrant determined by the sign of ax and ay. But often in physics, we want to know the acceleration at a single point, say right at P1. We are not looking for an average between 2 points, but exactly what is happening right now here at P1. So visualize it this way. Start with the expression a average is equal to delta v upon delta t, and imagine shrinking delta t to smaller and smaller values. Instead of measuring the velocity change over, let us say, 1 full second, we measure it over 0.1 second, then maybe 0.01 second, then 0.001 second, and so on. So we are still calculating the change using two vectors, but the time gap is vanishingly small. And you see, as delta t gets tiny, the second point P2 creeps closer and closer to P1. That is, as delta t approaches 0, the average acceleration approaches a definite value, and that limiting value is the instantaneous acceleration at P1. And just like with average acceleration, the x and y components of instantaneous acceleration are completely independent of each other. So let us put this to work to crystallize the concept by solving this problem. So what we have here is a hockey puck that slides across a frictionless ice surface, and at t equal to 0, its velocity components are vx is equal to 5 meters per second, vy is 2 meters per second. Then a little time later, at t equal to 4 seconds, its velocity components are vx is minus 3 meters per second, vy is 8 meters per second. And the question is, what is the average acceleration of the puck during this interval? And we have to find its components, magnitude, and direction. So step 1 would be find delta v component by component. So delta vx is equal to vx final minus vx initial, which is equal to minus 3 minus 5, which gives you minus 8 meters per second. Delta vy is equal to vy final minus vy initial, which equals 8 minus 2 or plus 6 meters per second. Step 2 is divide each component by delta t. That is, ax equals delta vx upon delta t, that is minus 8 upon 4, which equals minus 2 meters per second square, and ay is equal to delta vy upon delta t, which equals plus 6 upon 4, which equals plus 1.5 meters per second square. Step 3 would be to find the magnitude, and that equals under root ax square plus ay square, and when you plug in the values, you get 2.5 meters per second square. Finally, step 4 is to find the direction. The acceleration has negative ax and positive ay. So it points into the second quadrant. The reference angle from the x-axis is tan inverse 1.5 upon 2, which equals 36.9 degrees. And you see this is from the minus x-axis. And the angle measured from the plus x-axis is therefore 180 minus 36.9, which equals 143 degrees. And before we wrap up this problem, let us quickly do a sanity check to make sure the answer makes sense. Look at the x direction first. The x velocity went from plus 5 meters per second to minus 3 meters per second. That is, it decreased. So ax must be negative, and we got ax equal to minus 2 meters per second square. So check, that's correct. Now the y direction, the y velocity went from plus 2 meters per second to plus 8 meters per second. That is, it increased. So ay must be positive, and we got ay is equal to plus 1.5 meters per second square. So you can check this also, it is correct. Both components have the signs we expected. So the answer makes sense. So the puck's average acceleration has magnitude 2.5 meters per second square and points at about 143 degrees from the plus x axis. So here are the 4 key takeaways for this lesson. 1. Acceleration is the rate at which velocity changes, and velocity is a vector. If the direction changes, the velocity has changed and the particle is accelerating, even if the speedometer never moves. 2. The average acceleration vector points in the direction of delta v, not in the direction of motion. To find it, always do the vector subtraction. Delta v is equal to v final minus v initial. First, that is graphically by reversing vi and adding tip to tail, or numerically by subtracting components. 3. Instantaneous acceleration is the limit of average acceleration as delta t approaches 0. And 4. On perpendicular axis, the x and y components of acceleration are independent. Solve the x direction and the y direction separately, then combine at the end with a equals under root ax squared plus ay squared, and theta equals tan inverse ay upon ax, adjusted for the correct quadrant using the signs of ax and ay.